Hi, my name is Olivia Miller, and I'm part of Team Dusk along with Melissa, Nevin, Claire, and Justin. And today we'll be talking about our 470 design project, which was taking sugarcane and making jet fuel. In the market right now, jet fuel is commonly made from crude oil, and crude oil reserves are actually decreasing. And this is a growing concern because the aviation sector, which relies heavily on jet fuel, is increasing. So there's a really big push to find alternative ways to make jet fuel, and crude oil and fossil fuels that commonly make fuels for transportation or aviation are actually harmful to the environment. So this is a really big concern as well, to find a different way, a more environmentally friendly way to make these jet fuel products that are in such high demand. Biofuels are one big thrust for the alternative ways to make jet fuel, and specifically sugarcane. The nice thing about sugarcane is once it's fermented, it makes ethanol, and once ethanol is dehydrated, it makes ethylene, which can be combined into longer kerosene chains. So it's pretty simple chemistry. And in the market right now, sugarcane prices are low, which makes our process and plant feasible, but they're expected to rise by 10% over the next few years, which is something we had to consider before we went and designed this plant. So the main purpose of our experiment was to look at this biofuel process, taking sugarcane to jet fuel, and to see if it was economically feasible. The science was out there, and there are different ways to make this process work, but we wanted to see if this was economically feasible as a whole, to take this sort of small-scale lab testing data and see if it worked on the large scale. So that was our motivation for this project. Like I said, we were taking sugarcane to make jet fuel, and Sao Paulo, Brazil is one of the largest producers of sugarcane. So we chose a plant location that was in Sao Paulo for the readily available supply of sugarcane 6 months out of the year. So our plant would be designed, and our process would be designed around a 6-month growing time of cane juice, and then 6 months out of the year, when it wasn't the growing season, we would have another supply of cane juice outside of Brazil.
So the typical process to convert ethanol into jet fuel involves the condensation of an alkyl methyl ketone followed by deoxygenation. This process consumes 2 to 2.5 molecules of ethanol for every 1 molecule of jet fuel produced. This following table shows the range of jet fuel products that are produced from C8 to C16. Instead of using the typical conversion methods of ethanol into jet fuel, we decided to go with a relatively new technology called Vertimass. The Vertimass technology uses a single-step catalytic conversion to remove the water from the ethanol, leaving behind the carbons and the leftover hydrogen. This process is more desirable because instead of converting 2 to 2.5 molecules of ethanol for every 1 molecule of jet fuel produced, this single-step conversion does not lose much of the energy from the typical reaction. Instead, it uses only 1.6 molecules of ethanol for every single molecule of jet fuel produced. What is unique about this process is that it is slightly exothermic and does not require the addition of hydrogen. In this process, it is very important to properly distill and dehydrate the product before it can move into the catalytic conversion. What is also unique is that in this single step, the undesirable product of ethylene is minimized. And typically for each reaction produced, it is in the product about less than 3%. So using this Vertimass process in our scale-up, our plant has a capacity of 1,104 million gallons of jet fuel produced per year. This plant remains in Sao Paulo, Brazil, to utilize the local feeds of sugarcane. So our main specs for this project were to produce jet fuel range hydrocarbons in abundance with high yield and high conversion. We successfully did that using the Vertimass reaction, as pictured in the graph and as you can see in our conversion rates directly from our reactor. So one of the other specs that we were given was to produce around 5,500 gallons per hour of jet fuel. So instead of doing this, our mentors suggested that we use a different flow rate to calculate our mass balance. And in doing so, instead of producing around 5,500 gallons per hour of jet fuel, we are producing around 18,000 gallons per hour. Although this does not meet the original specs, the jet fuel range hydrocarbons in high yield were still produced.
This is our overall block flow diagram. As stated before, we have extremely high capacity in this plant with over 100,000 pounds per hour of our jet fuel product. In order to handle these, we had to make a lot of accommodations with our high flow rate throughout our process. Our first step in this overall process of converting sugarcane to jet fuel was separating the bagasse out of the sugarcane mixture with 10 centrifuge tanks. From here, we got our first major reaction when we are converting sucrose to an overall reaction to ethanol. After we convert the sugar to ethanol, we run it through 6 clarifier tanks in order to remove all the yeast out of the product blend. And then we move on to our 2 distillation columns where we want to separate the ethanol from the water that we have in our process up to specs in order to get it to our catalytic conversion through our Vertimass process. After this, we take it one more step to take it through a 3-phase separator to get our jet fuel product. These are our fermentation reactor specifications. Our overall reaction was going from sucrose, converting it to 2 ethanol molecules, and then the final step in the reaction was reusing the yeast to cancel out the catalyst and then to get an overall reaction of sucrose plus water yields ethanol and carbon dioxide. Our reactor, in order to achieve this, we have to up our pressure up to about 100 psi as well as 160 degrees Fahrenheit. We have 24 fermentation reactors in this process where each tank takes 24 hours for the fermentation to go through. Therefore, we have 12 to fill up during whenever 12 are going through the reaction. So in order to keep the process of our system in a continuous phase, we went with a plug flow reaction where the process can continuously react and produce product. We went with a plug flow reactor in this process for our Vertimass. The main challenge in this was obtaining reaction rates. Because this is such a new technology, it just started being studied at the Oak Ridge National Laboratory in early 2015. Therefore, we used the HYSYS reaction rate in order to obtain the necessary calculations we needed. After this was obtained, we used the design equation in the plug flow reactor, and we obtained a volume of 100,000 feet cubed. This was a large volume, and we wanted to reduce the length as much as possible, and so we went with a tube diameter of 6 feet, and we went with 20 tubes. After going through the necessary calculations with this, we got a length of 176.8 feet.
So after the catalytic conversion reaction, we have 3 phases coming out: 2 immiscible liquids and 1 vapor phase. Of the two liquid phases, the lighter liquid phase is our jet fuel product, and the heavier liquid phase is water. The vapor phase is ethylene and CO2. To model this separation, we used a 3-phase separator. We used various packing materials to easily separate out the jet fuel product from the water waste stream. After sizing this separator, we found that we could get a 99.7% pure jet fuel product. So now I'm going to go into a little bit about the economics of the project. So first of all, I'll talk about the capital estimate, which accounts for the inside battery limit, outside battery limit, team cost, escalation, and project contingency. So overall, the total capital estimate of the plant was about $7 trillion. The inside battery limit included initial equipment costs for process equipment, and the areas that accumulated the most cost were the fermenters because of the large amount of fermenters we needed, also the size of the fermenters, and the Vertimass process, which included 2 distillation columns, many heating elements, and a PFR reactor. The outside battery limit also accounted for a significant portion of the capital estimate. Probably the biggest cost in the outside battery limit was for environmental considerations, and this is because when we are separating out our jet fuel product, the wastewater stream contains a lot of toxic materials that are not only toxic to humans but also aquatic life, so we really need to consider wastewater treatment. Next, let's talk about the operating costs, which include raw materials, utilities, and fixed costs. For the raw materials, we found that sugarcane was 74 cents per pound of product, and yeast was 15 cents per pound of product. The utility costs were a large portion of the operating cost, and it was about $9,500 per pound of product, and about 99% of this cost can be attributed to refrigeration costs. The rest of the utility costs that we used were pump utilities, high pressure steam for heat exchangers, and for separation utilities. The fixed costs of the plant included plant labor and overhead, maintenance, property taxes, and insurance, and the total of these fixed costs were about $4.1 million.
So headed into the economic analysis, we knew pretty much immediately that this would not be a feasible process. So we have a raw material summarized here, and we have the catalyst, sugarcane, and yeast all normalized to the cost of jet fuel. And jet fuel is about 14 cents per pound, and at that price, what's called the raw material margin is negative, and it's very negative per pound of jet fuel. This means that we would need carbon credits supplied by the government for the customers that purchase our product in order for this production to be feasible. As was previously mentioned, our capital costs and operational costs were enormously high at $7 trillion and $4 trillion respectively. This is not practical at all and not realistic due to a couple of design mistakes, including cooling and inefficient separation that were somewhat due to software constraints, and this is unrealistic. So what we did was we did a little research on facilities that produced ethanol and facilities that converted ethanol into jet fuel, and scaled up our production accordingly to $1 billion and $137 million for capital and operation costs. This is what we used for analysis. It's not as close to reality as we would like, because it didn't go through the Icarus software, but it is much more realistic than what we obtained earlier, and it allowed for a better economic analysis. Using these values, we found that the jet fuel price required for a 15% rate of return was about $1.38 a pound, which corresponds to about $10.44 per gallon. Put that in perspective, jet fuel per gallon is about $1.14. And that would correspond to about $8 a gallon of carbon credits, which is a little high. Using this process, we have a cumulative cash flow of about $2.2 billion, net present value of $161 million, and a rate of return of 15%. And then our administration costs are 2.71 cents per pound. As I mentioned earlier, jet fuel is much too inexpensive at market price to be sold for profit at a conventional way, so we would need carbon credits. And we can see here that since crude oil and jet fuel correspondingly are very difficult to predict, we mapped out the rate of growth of those two products corresponding with the jet fuel price required to maintain a 15% ATROR. Along with the carbon credits required, we can see that as the rate of growth increases for the price of jet fuel, the carbon credits needed to maintain a profit go down. We conducted a variety of sensitivity analyses to see how our feeds and our capital and other aspects of the design affected the rate of return and the necessary price. This shown is a graph of the sugar price in correspondence with the jet fuel price and the ATROR with our initial jet fuel price at 15%. And we can see it's incredibly variable with sugar, as we raise the price from 18 cents to 22 cents a pound, and it raises the jet fuel price from 128 cents to 144 cents a pound. That is a very significant increase. We also did the same for catalyst pricing. It did not change as much due to the low cost per pound of jet fuel. We did the same with utilities. This really emphasized the importance of modifying our cooling and heating to be the most efficient as possible, well designed, so that it did not affect our rate of return. We can see that there is a very, very strong decrease with the increase in utilities per pound of jet fuel produced. Finally, probably the most important thing to consider is capacity, the operating capacity of the plant, because the sugarcane crop is so variable. And it could happen very many times where we are operating at lower than 100% capacity because our harvest could be low, or we could correspondingly have a very high capacity, and we would have to see how the rate of return would be affected and our jet fuel price that we would need to change. In addition, we studied a couple alternate processes that we could use to optimize the plant, including purchasing ethanol instead of making it and converting that into jet fuel, recovering ethanol from vapor streams, and recycling and selling ethylene to defray some of the costs needed to raise the jet fuel price. And we found that we could actually, at least we predicted that the value could go down to about 50 cents a pound of jet fuel, which is very significant compared to our original estimate. After completion of the financial estimate and our design, we would not be able to recommend this design or process at this time due to a variety of reasons, like the volatility of the market and the fact that the cost of utilities is extremely high, and this would have to be looked into much further. There was a lot of ambiguity as well with the catalyst process that was being researched, so there was a lot of assumptions that were made that cannot be relied on 100%. So in summary, this plant should not be built unless a lot of carbon credits are provided or sugar prices plummet while jet fuel prices soar. So that is our design project, and we would like to thank Professor McFadden and Greg and Josh, our mentors. They provided us with a lot of help, and we appreciate it. Thank you.